Greetings, fellow seekers of knowledge, from the smallest quantum to the grandest galaxies. Welcome to Paperledge, where we slice open the latest scientific papers and see what marvelous, mind-bending insights spill out. I'm Ernis, your guide through the sometimes dense, always fascinating world of academic research. Ahem. Today, we're not just skimming the surface of a paper, we're diving deep into a newly charted ocean of artificial intelligence and machine learning. We're talking about making LLMs. Those digital brains behind your chatbots and AI assistants, even more intelligent by giving them a super-sized memory. We're tackling a paper titled MTraining, Distributed Dynamic Sparse Attention for Efficient Ultra-Long Context Training. Now, you might be thinking, ultra-long context? What in the name of Rick Sanchez's interdimensional cable is that? Well, context, in this case, is like the memory of an LLM. The longer the context, the more information the model can consider when making decisions or generating text. Think of it like this: a short, context model remembers the last few words of a conversation, while an ultra-long context model remembers the entire history of your interactions. The implications are enormous. Imagine AI that can truly understand entire books, analyze complex code repositories, or even manage long-term projects with a complete understanding of the past. But there's a catch, of course. Processing all that information is incredibly computationally expensive. It's like trying to run the entire internet on a calculator from the 1970s. Not gonna happen. That's where MTraining comes in. This paper introduces a clever new technique to make ultra-long context training much more efficient, particularly when using multiple computers working together. A distributed setting, as they say. So, how does MTraining pull off this seemingly impossible feat? Well, buckle up, because we're about to enter the memory palace. Picture a sprawling digital city, each district representing a different aspect of MTraining. Our first stop. Dynamic Sparse Training Pattern. This is the city's clever zoning system. Instead of trying to process every single bit of information, MTraining focuses on the important bits. It's like having a super-efficient librarian who knows exactly which books and pages you need, ignoring the rest. The key here is sparsity. The researchers discovered that attention matrices, the way the model focuses on different parts of the input, are naturally sparse. Most of the connections are weak or irrelevant. MTraining dynamically identifies and focuses on the strong connections, dramatically reducing the computational load. Now, this is where things get really interesting. The researchers noticed a fascinating pattern in these attention matrices, a vertical/locality pattern, as they call it. Imagine a cosmic barcode, with strong vertical lines and diagonal slashes. This pattern is related to how the model uses relative position embeddings, specifically something called ROPE or rotary position embeddings. These embeddings help the model understand the order of words in a sentence, and they create this unique barcode structure. The next stop in our memory palace is the Balanced Sparse Ring Attention District. This is all about teamwork and efficient communication. When training these massive models, you often need to distribute the work across multiple computers, like a team of construction workers building a skyscraper. But if the work isn't evenly distributed, some workers will be idle while others are overloaded. This is the problem of worker and step level imbalance. MTraining tackles this with a clever technique called striped ring attention. Imagine a circular assembly line where each worker is responsible for a specific section. MTraining ensures that each section has roughly the same amount of work, keeping everyone busy and maximizing efficiency. It's like a perfectly choreographed dance of data. Finally, we arrive at the hierarchical sparse ring attention district. This is the city's advanced communication network. In a distributed setting, computers need to communicate with each other to share information. But if the communication channels are slow or congested, it can create a bottleneck. MTraining addresses this by creating a hierarchical communication structure, prioritizing communication within the same neighborhood or node, and only using the slower internode connections when absolutely necessary. It's like having a local postal service for nearby deliveries and a long-distance service for everything else. So, what's the result of all this clever engineering? The researchers tested MTraining by expanding the context window of a model called Qwen 2.53b from tokens to a whopping tokens. That's like giving the model a photographic memory. They found that MTraining achieved up to a 6-fold increase in training throughput compared to traditional methods, while maintaining or even improving accuracy on a variety of long, context tasks. They also validated the approach on another model called Llama 3.18b, instruct with larger scale and different model architecture. In essence, MTraining is a significant step forward in making ultra-long context AI a reality. It's not just about building bigger models, it's about building smarter models that can truly understand and process vast amounts of information. As these models continue to evolve, they have the potential to revolutionize everything from scientific research to education to creative expression. And that, my friends, is the essence of MTraining. A fascinating blend of clever algorithms, efficient communication, and a deep understanding of the underlying structure of attention. I hope this journey through the memory palace has illuminated the key insights of this paper and sparked your curiosity to explore further. Until next time, keep questioning, keep exploring, and keep pushing the boundaries of knowledge.